Sajal was a PhD student with jointly with Arnav and me, and he finished his PhD in 2012. After that, he was a postdoc at UPenn. He was working on sort of topological properties of semiconducting nanometers, specifically silicon, and sort of studying galvanic effects there. He did his second postdoc at Rochester. He was working with Nick Wamibakas's group, mostly discussing or studying transition metal dichalcogen and their optics. And I think he's going to talk about that. So right now, he's an assistant professor at IIT Kharagpur for the last year.
1 year.
1 year. And he's setting up a new lab here. And he's going to tell us some of the work that he just came out, and it's kind of some part was finished up, but he was in India now.
Yes.
Okay, welcome, Sajal.
Thank you, Mandar. And it is a really great pleasure for me to present this talk. I thank the organizers and also Mandars to arrange this Infosys seminar. So today I'm going to discuss about the light-matter interaction in two-dimensional systems. So these two-dimensional systems, so there are actually few groups in TIFR also, Manda's group and Arnav's group. Also, some works are going on looking at electronic properties as well as growth. So today I'm going to discuss about basically an introduction to how these materials are interesting, and so I'm going to talk about a little bit different aspect of these materials that can be used inside the laser. That can be used inside a microcavity to realize very interesting material system, which is known as exciton polaritons, that is formed by, it's like a half matter, half light particles. And the interest in this field is driven by the possibility that this exciton polariton is such a system that can offer a condensation, for example, Bose-Einstein condensation, even superfluidity, very close to room temperature. So I'm going to discuss how. And so as a result, these systems, these also have a lot of defects. That means that it has electrons that you can control by gate voltage, so that this system can also be used as a many-body system where you can study many interesting physics. So before that, I'm going to acknowledge all the group members that were involved in the work that I'm going to discuss today. So this work was mainly experimental work, was mainly done while I was in postdoc in University of Rochester with Professor Nick Wamibakis, is the PI for this project. And there are Chitpalima Chakraborty, the graduate student there. She was also a project student before he joined in the University of Rochester in Mandar's group. So this is a newly joined graduate student at that time, Claude and Kenny. So Kenny graduated when I just came back. And there is another group member from the Institute of Optics. So this is a student, Trevor, and his PI and his supervisor, Professor Gary Wicks. And so after I finished this experiment in the University of Rochester, I came back and joined at IIT Kharagpur, and we were still trying to figure out the theoretical part to understand the experimental results that we just got. So I had an interaction with Professor Subra Bhattacharjee. So while he was visiting at IIT Kharagpur, and had a discussion about this problem, and then we came up with a model that actually explains that. So these are all the collaborators. Now, so this is the outline of my talk. So I'm going to talk about these two-dimensional semiconductors, mainly these transition metal dichalcogenides, and how these, so the aspect of excitons in this material. These excitons, when we embed these two-dimensional material in this microcavity, so we get these exciton polaritons. We'll discuss about microcavity. will give a little bit the background historical development of this field. And so this material, so basically this is an discovery of new materials, but the cavity physics is already old. So basically it's a new material in an old cavity. And then we'll so basically discuss what this new material can actually give us, and what has been achieved and our new results, and then we'll discuss the future directions that we can go in this field. So, so when I was a student here, so it's in my undergraduate, so there was the graphene actually the field the discovery of this graphene and the quantum Hall effect was, I think that around that time in 2005 it was big at that time. And then when I graduated around 2012 when I postdoc, so it's now there are different kind of two-dimensional materials that people were looking at. So one of these is graphene-like structures. So and that actually is the main experimental works that has been published around that time is around 2012, and it's still going on. And so this is a brief introduction. I know that many of you are familiar with the honeycomb structures, but I think it will be good to discuss it from the beginning, how these honeycomb structures actually giving rise to very interesting electronic band structures. So this is a triangular lattice, and if I have another triangular lattice such that it forms a honeycomb structures, and then so basically we so this is a honeycomb structure and made of two sublattices A and B, and that so these honeycomb structures have in reciprocal space you can draw the Brillouin zone, which is also an hexagonal, and it has very two particular so these points are very interesting points in the Brillouin zone, and we know these values are around 4 pi by 3a, and this is minus k. And then we'll use, so people have done a long time ago, in around 1947, actually done pen and paper calculations of these honeycomb structure, electronic band structure into these honeycomb lattices. And what has been found is that if I do a tight binding approximation, and if I write down the full Hamiltonian without any approximation, we can show that if I put the value of this k and k prime, the energy gap at these k and k prime vanishes. And then if I zoom in this part, and if I expand that Hamiltonian near one of these k and k prime, where let's say k equal to capital K plus q, so that q tends to 0, q is very small, then we can write down Hamiltonian in this form, where then if I just diagonalize it, we get the band structure, which is very close to this k and k prime. It's linear, right? And now if I have this sublattice symmetry, because in case of here we had A and B sublattices, they are occupied by the same kind of atoms, carbon atoms, so their on-site energies are equal. So the orbits that were participating in the hopping, their energies are equal. Now if I change that, if I change one of these sublattices to some different atoms, let's say A and B sublattices are occupied with different set of atoms, so that the on-site energies are different by E plus delta E and E minus delta E. Then we can actually get it, so basically the Hamiltonian will change by additional term here, and that is basically will give rise to the energy dispersion that looks like this. So now you'll see that there is no point in the Brillouin zone where the band gap vanishes, right? So now this is basically what will happen at those k and k prime points. We'll open up a band gap just because the sublattice symmetries are broken. And this will also give rise to an interesting effect, because at these particular points they have non-trivial pseudo-spin, non-trivial pseudo magnetic moment associated with very close to k and k prime points, which was 0 in case of graphene because of the sublattice symmetry. And now, so this material become very now interesting because this is a direct band gap material, and it is very interesting that as soon as, so this material, if I consider a bulk material made of same atoms, we will see that this will not happen, and this direct band gap will no longer be valid, and people have observed, and this is well established, that if you go to bulk, then there is no electronic excitation. Is very difficult to make, so it will not emit light. So if I excite it by shining light or by any other means, it will not produce any light. But if it is a direct band gap, it can actually, what you can do, you can basically excite the electrons in the valence band into the conduction band, and then it can actually form an electron hole pairs. So they will interact with Coulomb interaction in 2 dimension in the plane of this material, and that will basically form a hydrogen-like system, right? So these are called excitons, and these excitons, since these are confined in 2 dimension, the interesting thing will happen because the electron and hole confined in 2 dimension, their energies will be defined by this factor, just like a hydrogen atom in 2 dimension. You notice a factor of -1/2, n minus 1/2 whole square. So if it was a 3-dimensional case, then it will be, there will no half factor here. As a result, you get a binding energy that is 4 times the Rydberg energy, and that will give you a binding energy which is experimentally verified, that is 0.55 electron volt, which is huge in the sense that you can even get excitonic state, stable excitonic state even at room temperature, because room temperature is around 25 milli-electron volt, right? So you'll be able to get, so you'll be able to see these excitons even at room temperature very stable, right? And now, so if you, so this paper actually talks about an experimental verification of that. So they actually measure this exciton binding energy by measuring their, so they perform scanning tunneling spectroscopy to measure the band gap of this material, and then they perform a photoluminescence. So this is when they measure the direct band gap of this material, which is large, 2.26 electron volt, and when they do the photoluminescence, they get a lower value, 1.62 electron volt. And as a difference, you will get the binding energy of this excitron, which is theoretically calculated 0.65 electron volt, but when they measure experimentally, they get it 0.55 electron volts. Also, these binding energies of these electrons, these excitons, also depends on the substrate, on which substrate you are putting, because the screening will be different. And they had actually also calculated it in, if you produce a no substrate, if you give a substrate which is bilayer graphene, their binding energies are different. Okay, now the other interesting species that exist in these material is that you can also form bound state of this electron of exciton with another electron. Suppose I have an exciton gas, and if there are free electrons, if I introduce some doping, either electronically or chemically, those free electrons will basically form a bound state. Now these bound states are also stable. It isn't just like an hydrogen ion. Hydrogen ion is very stable bound state, and this charged exciton that I am talking about, a bound state of exciton and electron, these are also very stable bound states with a binding energy of 30 milli-electron volt. And this is an experimental paper where actually what they do is they first observe the A and B excitons in this material. So the origin of this B exciton is this material also has spin orbit coupling, as the valence band also splitted, and so they are basically defined by that spin orbit splitting energy. And so this is an A exciton, so we are only focusing on A excitons. This is an absorption curve, but in photoluminescence, which is not seen in which is not visible in the absorption curve, in petroleum instance curve you see two peaks here. They are so one is separated by the other by 30 millielectron volt below this A exciton. So this is basically the bound state of the exciton. So this is called trion peak. So there we have two resonance peak in this material, and by changing the electron concentration. So if I now remove all the electrons, then we will only have excitons, right? And if I have exciton and then if I increase the electron concentration, so more electrons will form bound state with exciton and they will become trions, which is a charged excitons, right? So you can change from trion, full 100% trion to 100% exciton, and in between we'll have both trion and exciton mixing, right? Mixture. So as a result, you'll have you can get experimental curve like this, which is a two-dimensional plot of intensity, which is a color plot as a function of gate voltage and energy, where you can basically see that this is the neutral exciton at 0 gate voltage. As you tune the gate voltage from positive and negative direction, you get another resonance curve, which is basically charged exciton in minus negatively charged exciton and positively charged excitons here, right? But now, so this is the outline of the so far.
Sorry, question. I don't know about it. Why is the showing up in the absorption?
Yeah, that is actually very interesting question, and that is the reason people say is because so the exciton, when it decays, it produces a photon, right? So exciton decays and it produces photon, and photon also absorbs and produces an exciton, right? So this is two are bosons, right? Exciton. So roughly these are exciton is boson and photon is also boson. Now for trion, this process is a little bit difficult, because now it also have to take care of the momentum of the electron that it emits, right? So